And so let's start by sharing the screen and just walk you again through the web page. So here's our course web page. And yeah, I guess we don't have to go through that every lecture. So here's our schedule. So we're here. So just like last time, I asked you to watch the Berkeley lecture. So you just always click on this online video, which is right here. It's really well done, and the overlap with what we're presenting these weeks is very big. So basically, I think this is for the benefit of everybody, that you guys watch it, and then we can make this lecture more like a consultation and more interactive. So I assume you all watch this. It's going to be the same for the next lecture before the Easter holiday. So again, you have a link here. So that's the Markov decision processes 2 that you're supposed to watch before the next lecture. I guess I use my own slides to sort of give a quick recap and give you an opportunity to ask questions. If you already have some from watching this lecture from Dan Klein, then you can already post it in the chat. Okay. The slides I'll be presenting today are here, and just after the lecture I will add a version that has also the notes where you have extra information. So I'll stop sharing, and I also stop my camera such that the slides are bigger. Okay. So do you find the lectures from Berkeley, high quality and entertaining? Do you like them? Okay, so yeah, it seems so, and yeah, indeed. So these guys also they do, of course, they are at the top university, and they also do research in these areas. So I think really they are in a good position to deliver, to this content in a nice way. Okay, so sequential decisions under uncertainty, Markov decision processes. So this is the the world that they also used in the Berkeley lecture. It actually comes from the Russell and Norvig book, and it's a simple grid world. The new thing, so as I always say, we sort of will building up the complexity. So at the beginning of the course, we were dealing with these, search problems. So, you would be asked to find the quickest, the short route, for example, from start to the +1, which in this case would be quite an easy task. And what we will introduce now is what you see here on the right. So basically, your agent, you command it to go forward, and in 80% of the cases, for example, it will go forward. But in 10% of the cases, it will go left instead, and in the other 10% of the cases, it will go right instead. So what we're introducing is uncertainty. So basically, it's stochastic outcomes of actions. So that even if you tell it to go forward, this will not always be the case. And this is quite a complication, which we will have to redesign the way we're dealing with these problems. So that's basically in a nutshell, what has changed. So the world is still observable. That means, we know in which state we are, and we sort of have the map, but it's not deterministic. So it's stochastic, that the outcomes of actions, and we cannot rely on them 100% anymore. So that's basically what has changed. There's a notation, of course, that is that goes along with it. So we need a transition model, which we will denote like this. We have a state, we have an action, we have the state where we get from the original state, and it's essentially a probability of getting in S prime state, given that I was in state S and I performed the action A. So probability that A in S leads to S prime. So that's how we notation we use. That's identical with what was in the Berkeley lecture. This is a motivation slide. So like you have two options: either you go this way or you go around, and this, the uncertain outcome of actions is, if I choose to go this way, which may be the shortest path, it may not end up well, because this whole thing may collapse and I will fall into some kind of crevice in the glacier. So that's basically the motivation that we're, that we're dealing with. Right, and now, so the biggest change now is that before, it was fine to deliver basically a sequence of actions. So the plan, how to go, from one town to another, which road to take. However, this will not work anymore now. So what is the problem now? Why a sequence of actions is not enough in this case? So the word is now stochastic. So when I tell the agent to go from here to here, it may, but it may also not go there. So if my sequence of actions is right, right, up, right, and I hope to be in the blue square, which has the reward, why is this not enough? Any ideas? Okay, so the question is, if this was a planning problem, find the search, find the quickest route from this square to this square. The solution would be a sequence of actions: right, right, up, right, let's say. Now the environment, so the effects of actions are stochastic, so they are not deterministic anymore. That means if I issue the command right, I may go right, let's say 80% of the cases, but let's say 10% of the cases I will end up left. So as a solution to the problem, which is still find the quickest route, let's say from here to here, why is it not enough to have a sequence of actions which is fixed? Why is it not enough to just up, right, right, up, right? And feel free to also join the lecture with your microphone on to make it more interactive. But I'd say but the chat is also fine.
Okay, so I would say that we need to consider the probability as well.
Yes. So right. So the problem is that the sequence will only hold as long as it really happens what we command the robot to do, because as soon as the outcome is different, which may well be the case, so I command it to the right, but I end up here, well then the rest of the sequence, which in this case was right, up, it doesn't hold anymore. It doesn't make sense anymore. So as soon as the environment is not deterministic in this sense, then it's not enough to have the sequence. Instead, what we need is basically we need to know what to do in every state. That means we need an action to do in every state, because we can essentially end up in every state. This was not the case before, because we would just plan, let's go like this, and that's what would happen. But now that the uncertainty, on the action part can bring us basically anywhere, we have to have a plan, or we have to have we need to know what to do in every state. So that's what changes. And this new thing that we need is called policy. Okay. So the policy is a mapping from the state space to actions, which is something like this. So these are terminal states. So these are states that, basically you get a reward or you get a penalty, but you're exiting the world. And these are normal states where you can do actions. And this, what you see here with the arrows, is the policy. That is, it's a policy. It may be the best policy. It may not be the best policy, but it's something that tells you in every state what to do: move up, move right. So this is what you see here. And yeah, so as soon as we have this non-determinism there, we need a policy. That means for every state we need to know what to do. So that's the idea. Right. Okay. Typically in search, the final outcome was reaching the goal. In games, like in the adversarial search, the reward was only at the end. So we won the game, or we lost, or it was a draw. Here we're going to change it a little bit, and so these are the terminal states, which is somehow like before. And this one gives you +1, this one gives you -1. But what we will introduce in addition is a living reward, so-called, or a living penalty. That means for every move, it costs something. It may be positive, it may be negative. This will have consequences. But the idea is that we basically want to motivate the agent to go, as quickly as to the goal as possible. And so that means, you can imagine it's an agent that, consumes fuel. It's a car or something. So every move within the environment costs a little bit of something. So we have to basically reshape the problem in this way. So reward function is a function. Depends, the different authors frame it in different ways, but the most general one is this one. So it's a function of the state where you were, the action you took, and the state where you end up. It's a bit like you're sort of paying for a particular transition. And yeah, this is the particular formulation we use in this case. And yeah, a sort of technicality is that in the terminal states, you still have to use an exit action to actually get the reward. I think this is implemented in the MDP agents Python program that you will be playing with. It really is. It's more like a technical thing. Right. So basically, yeah, it's a generalization of the search problems. Yeah, so this, we've seen this before. This is how we basically, that's the notation for the non-determinism of the actions. So we have states S, we have actions A. This is the transition function or model, reward function. So we went through that. Markovian property. Given the present state, the future and the past are independent. So in other words, the action depends only on the current state. So it depends where you are in the, let's say, in the maze right now. It doesn't matter how you got there. So that's important because it sort of allows you to cut off the past, which otherwise, would make the state space much more complicated. It would increase the dimensionality a lot. Yeah, and this is also the same in search. Okay, so here's the first task, like an interactive task for you. So here you see 3 of these, of the same maze, of the same kind. And the arrows, they show the policies. Okay, so that means they tell you in every state what the agent should do, optimal, best policies. And here are different reward functions, but it's been basically there's a permutation between the environments and their reward functions. So the task for you is to find which reward function belongs to which environment, and so how you read this. So this 1 and -1, that's the same. These are just these terminal states, the reward there. But what is different is the living penalty. So this is the one we saw before, that for every move, let's say from here to here, you get a minus 0.04. Here it's even less, the living penalty. And here it's really big. So basically it's even bigger than the penalty you get into this wrong exit. Okay. And you don't need to calculate anything, but just use your common sense to sort of think which belongs to which. So basically you imagine the reward and then how you would adapt the policy for the agent if this reward function is different. So I'll start the quiz, but take some time to think about it. So the way to read this is that AA means that that to this environment you would assign this reward function, right? AB means that for this environment it should be reward function. Okay, so Elisa, you want still some time to finish it, to give it a try? Okay, good. So let's publish it. Right, so yeah, half of you got it right. So it's indeed C. Does anyone want to explain, why is it like that? It's okay. It's okay. So I'll try. So this is correct. And so A, B, so this is the reward function that belongs here. BA, so this belongs. Okay, let's start with this because this is quite an extreme example. B, let me see. No, sorry, BC and CA, right? Okay, yeah. So the sort of normal reward living penalty would be this minus 0.04, which is this B, and that belongs to this world. So what does the policy look like? So basically, if here, you're supposed to go here, which makes total sense. If you're here, you're taking a, and the reason for this is that it's dangerous to go around around this square, right? Because there's always this 10% chance that you will fall into the -1, and you don't want that. So it's kind of, we call it a conservative policy, that it sort of avoids this risk, and so it prefers to go around. Still, in this square, for example, it goes up. It tells the agent to go up, which is sort of expected, but it's running this small risk of falling inside. Okay. Now, this environment, it's very similar to the policy, but there are two squares, very different, which is this one and this one, where it's doing strange things. It hits the wall, which is, by the way, something I probably forgot to explain. So the rule of this maze is, if you go into the wall, you basically stay where you are. And so what the agent is doing there is that rather than going up, which would be intuitive, it prefers to go into the wall, and it's waiting, for the chance to bring him either here or here. But in both of these cases, it is absolutely sure that it will never fall here, because the stochasticity will never bring you in the opposite direction, only left or right, clockwise or counterclockwise from where you want it to go. So yeah, and same is here. Rather than commanding to go here and risking ending up here, he prefers to hit the wall until there's a 10% chance that eventually it will bring him here, but it will bring him there safely. So it's a super conservative policy, and you may already guess that this has to be this kind of reward function where the living penalty is very, very small, so it doesn't cost you much to just bang against the wall and wait until you safely get forward. And finally, there's this CA. And yeah, so this is a weird sort of policy that, because the living penalty is so high, it's better to just hit the nearest exit, no matter which exit it is. So it's to just get away right away and get a -1 rather than spending time. Which the metaphor you can imagine, it's like, let's say your robot is a firefighter robot, and the floor is burning, and he really needs to exit that floor, even if there's some kind of ramp that let's say your robot has tracks, like the robot that we're doing research on, or this would be stairs, which are not nice for your robot, but it's better to just fall down the stairs than if the let's say floor collapses under you. So that's how it all comes together in these three cases.
Maybe may I ask a question?
Absolutely.
Well, in the option B, why in the right bottom corner we don't go left?
Here.
Yes.
Yeah. Right. Yeah, because if you go left, there's a 10% chance you end up here in the -1. And since the B belongs to this reward function and the living penalty is very mild, it's it's better to just hit the wall. And if in 80% of the cases you will end up here, in 10% of cases you will go this way, which means also you will end up here, and in the only other 10% of the cases you will go here. So you have to wait for that, but you are absolutely sure that you will not end up here, and that's what you want. So basically you can afford to spend time because the living penalty is small, and this penalty kind of outweighs the living penalty. So that's why it's the same like here, but it's just that you're avoiding to end up.
Okay, thank you. I have thought that the probability is just when I go up that I can go left or right, not for every direction.
Right. Okay, that's a good point. Right. So it's a sort of So yeah, this means that this is with respect to where you want to go, and but it counts in every direction. So so let's see. So if for going down. Okay, I have to use the ink somewhere.
Well, now everything is clear, so I'm fine.
Right. Okay, that's fine. But anyway, so for going down, it would look like this. There would be small arrows here, and So yeah, you can rotate this in every direction. So, or for going left, we have this 80% here, and we have 10% here and here. Yeah, so the same for going right. Yeah, so this is a good point that we should explain this clearly from the beginning. This is, the uncertainty is for every direction you go, and I think this is also going to be the case in your practical exercises. So it counts in every direction like that. Thanks, Lukáš. So Rufat is typing something. So is the link the best case for us? The smaller it is. Yes. Yeah. So yeah, for the agent, definitely. Well, so the reason we will shortly see that there is this sum of rewards that sort of defines the problem that matters, and the reason why we introduce this living penalty is that we don't want the agent to just wander around the maze and get positive rewards. We want to basically motivate him to go to some exit. So that's why we basically introduce that. And but how big the penalty is will, as you see, influence the strategy, the policy. I don't get why A, B, and B, C. Well, A, B, and B, C. Well, we will see. You will learn basically how to do the calculation, okay? But just using common sense here, the living penalty is bigger. Okay, so that means if I waste a lot of time, I will accumulate negative rewards that will potentially outweigh the positive reward when I get here. Okay, so I don't have as much time, so that's why I sort of have to make reasonable actions. For example, from here, go towards the positive exit. While here, if the living penalty is very tiny, I have time to do stupid things like, banging against the wall until it gets me here. So basically, I have sort of 4 times more time than here. And that's why in the calculations, it sort of comes up in this way that it's better to really be super conservative and -1 at all costs, and rather, hit the wall and wait until it gets me somewhere safe. So that's the idea. Is it clear, Rufat? Right, exactly. Yes, that's a good point. So Rufat is writing, the arrows don't influence the living penalty, but the other way around. Right. So the reward function is part of the problem definition of the environment and of this Markov decision problem that we're solving. And the arrows are what we're supposed to find. This is called the policy. Okay. And indeed, so our task is to find a policy, so like find a plan. If we use the old terminology, in this case we call it the policy, and the only policy will be different depending on how the reward function is set. So yes, this is another good point. So it's the matching works in this way that this defines the problem, and this is the outcome. This is the policy. Right. Does it make sense, Rufat? Wonderful. Okay. So let's move on. Right. So there are utilities. So yeah, we had it in the last lecture that there are these preferences, and then there are utilities. This is a sort of, again, a rather technical thing that we don't have to go into the detail. It's the same argument, if you prefer something over something, then there is a utility function that can actually assign the actual rewards such that it's consistent with your preferences. And the notion of stationary preferences means that that change over time. So basically, if I'm in some state, so there is a state sequence like this one, and if I prefer the state sequence over another state sequence, then even if I add something to the beginning, this should still hold. So basically, so the preferences don't change with time. And so the reason why we're talking about this is we will be summing up the rewards as the agent, moves in the maze. And then there are two formulations of the problem. One is finite horizon and one is infinite horizon. And so the finite horizon means you will have only 10 steps. And that may create some problems because the policy may become non-stationary. So if we go back, if I know I have only, let's say if I'm here and, let's say I'm here and I know I have only 2 steps left, then, my only chance is to go here and here, right? So basically, while if I have a lot of time and it's this environment with the mild living penalty, I have time to do this and I will eventually get there, right? So, but if I know that I have only the 2 steps left, then I will also have to change my policy. So basically, let's say if I have 100 steps left, I might be the optimal action, but if I have only 2 steps left, it will change and I should go up. So the policy in this case will be non-stationary because it will change depending on how much time is left, which mathematically is not a nice thing for us. So instead, we will be often dealing with these infinite horizon formulations, which means that the agent has infinite amount of time. But for this to work out, we need to introduce an additional thing, which is that we will have to discount the rewards. So what does that mean? That means that the rewards in the future will count less. They will be discounted by a factor gamma. And so more in the future they are, we do basically gamma to the number of time steps into the future. So it's an exponential decay. And the mathematical fact is that if something decays exponentially for gamma smaller than 1, is that this geometric series has a finite sum that is defined like that. That means even though the horizon is infinite, and the sum of future rewards is finite, and that's an important thing, right? So the benefit for us is that the policies will be stationary, but the sum of rewards will be finite. So that's basically that's the problems we will be mostly dealing with. Right. Yeah, this is just some basically sort of technical ways of expressing the. Right. So let's recap the notation. So set of state S, set of actions A, there are transitions. So those are actually the conditional probabilities, and then there is a reward function and discount. Okay. Now, the Markov decision process quantities, there is a policy, which is a mapping from states to actions. And then there is a return or utility of an episode, which is a sequence, and it's a sum of possibly discounted rewards. So that's basically what we need. And value functions is something important that we will be dealing with. So this is how the notation is introduced. So the environment is stochastic. So that means that the return of an episode is easy. You just have this sequence of moving in the maze, and you just count up the rewards which you may discount. But something more general and more useful is an expected return of a policy. Expected means that take probabilities into account. It's like expected value in probability. It's basically a weighted average, taking into account the probabilities of events or variables. So this is the notation, the utility given a policy. That means something that tells you in every state what to do. From that state is the expected value, expected return given the policy. And this means that you're just executing the steps. The more steps you execute, the more discounted they will be. And this is this return basically of that, this is the reward of, in those particular states that you're receiving as you go. Yeah, so I don't think we have to spend too much time in this notation, and it's also consistent with the Berkeley lecture. Action value function or Q function is the same thing, but the difference is that your next action has been fixed. So it's been added here and it's been added here. And that's something that will sort of help us in the algorithms that we will be learning. And because after all, the algorithms are about deciding, the next action. And this kind of the Q function will help us out, because it basically it's a sort of local thing that that from the expected some future rewards depending on which action you choose from where you are right now. Yeah, I guess this is quite abstract, so probably it's better if we look at examples. But it's been also explained by Dan Klein in the lecture. So let's move on. So the value, and so the star, this always means optimal policy and optimal value of a state. So if the policy is fixed, then I can assign values to states, and that means that's the expected, possibly discounted sum of rewards, assuming optimal actions or assuming actions of a fixed policy. But so as soon as I know what to do, and even if there is uncertainty, this I can deal with this, expected return. That basically, this is similar to the chance nodes that you had in the Expectimax. This is also, I think, explained very nicely in the Berkeley lecture. So even if there is this chance, this is something we can deal with, and we can calculate an expected value for every state. Our ultimate goal is rather the policy, but the values can be, they are sort of, two sides of the same coin, and the values, are instrumental also in getting to the optimal policy. Right. So here you see that's our familiar maze, and just a couple of things. So in this case, the robot is deterministic. So that means it follows the policy, right? There's no uncertainty. Gamma is the discount factor. It has to be smaller than 1, but we can sort of afford to have it very, very close to 1, okay? And this is the reward function, also the one with a sort of reasonable living penalty. This epsilon is something you will encounter in the code. It basically tells you when your algorithm can stop. So basically, you're estimating the values, say the value functions for every state, and once those stop changing, or once the changes become very small, you will terminate. So you will see that the way these algorithms work, they iteratively improve something in the policy or the value or both. And you can basically do this forever. But once the changes are small, you can basically say, okay, yeah, I'm fine. So that's basically the epsilon. Okay. Now, so yeah, and here you see the policy, and here you see these are the values. Okay, so this is the value of this state given this policy. So one thing you can notice is the closer you are to the exit, to the positive exit, the bigger the value. And so you can very clearly see here that the effect of this living penalty. So the value of here is 0.96 because I will pay only one living penalty. The value here is another 0.04 less because I will have to pay 2 living penalties until get here. So you see the nice propagation of that. And yeah, so you see that very clearly because the robot is deterministic, right? So let's move to the next slide. Everything's the same, but the robot is non-deterministic. And the policy is, let me check, is probably still the same. No. Okay, so let's watch it closely. So the policy has changed. Right. So here, for example, in the deterministic case, here this was the shortest path. So why not taking that, right? And now as soon as we introduce the non-determinism, which is the one we saw before with this 80% of chance of following the command, we prefer to go around, right? So this is one thing that changed. And the other thing that changed is that the values are much smaller now, right? Which is, for one, it's because, you may be very unfortunate and end up here, but also because there you get more of these living penalties, because basically, even though, you really want to go like this, there's this 20% of chance that you will not go there, and you either end up staying because you hit the wall, or you even, for example, you want to go here, but it will send you there. And that means you will accumulate more of these living penalties. And, the effect here is smaller because, you have only one step until the end, the exit, where sort of the non-determinism plays against you. But here, you have 1, 2, 3, 4, 5 times you sort of have to, roll the dice and see if the agent obeys what you commanded it to do, and that's why the rewards are so going back here it was, let's say, 0.8, and here it's 0.71 because you accumulated more of these because you were unfortunate. Right. Okay, and this is the case that we also saw before, the one with the very mild living penalty, which also changes the policy. These were these, cases of, just hitting the wall rather than risking falling into the pit. And yeah, overall the values are higher because basically, you see this propagation of the living penalty is, it's the living penalty is smaller. The non-determinism is the same. So yeah, so you see that the non-determinism obviously shapes the policy and the value function, but also the reward function shapes also both. And yeah, so this is the connection basically to the expectimax that we went through last time. So the non-determinism is basically like a chance node that where you have to roll the dice. In this case, you basically it's your robot that rolls the dice, when interacting with the environment. So yeah, and this is nicely explained in the Berkeley lecture. So this is the connection with expectimax. This is the difference between this value of a state of a Q state. As we explained, the Q state adds that you have committed to do a particular action from the state where you are right now, but for the rest, you're acting optimally, or you're following a fixed policy. But the difference is that in that particular state, you're not maxing over the actions, which is so the value, to find the value, it's really that's the connection with expecting max. In this node, you're choosing the best action for you, and the rest is the chance node. So there you have to basically take a weighted average, taking probabilities into account, and either you're maxing right from the beginning, or you fix one action, and this is this Q value, which will become more clear as we look into the algorithms. So one result that is basically behind all the algorithms that we will see is this Bellman optimality equation, and it's basically one ply of the expecting max. So the value of a state, I have to max over the actions that I can take from that state. Then I have this weighted probability over the successor states. Those are the S prime. And so value is summing up the rewards, right? So this is the reward of the transition, basically, I will take. It's weighted by the likelihood that this will actually happen. And here is the value of the successor state, and which is discounted by gamma. And so the point is that rather than doing the whole expecting max, which can get you, very, very deep, you basically can sort of cut it here, because you will be computing the values also for the other states in your environment. So here, let's say you are here, this is your S, this is, S prime. So S prime will also have a value, right? We saw that basically the goal is to calculate the value for all the states. So they have a relationship between them, which is expressed by this mathematical formula, the Bellman equation. And this is a very important result, because it basically allows you to skip doing the whole calculation in expecting max, but by relating one value to another, by this equation, you can develop, let's say, shortcuts which are useful for the algorithm. Question from Lukas: what is the difference between living penalty and discounting? The living penalty is contained in V star, but discounting decreases the value of entire V star. Right. Discounting decreases the value of entire V star. That is correct. Well, the living penalty is in here, right, in the reward function. So the living penalty is state dependent. It's a state transition dependent. So basically, we call it living penalty, and we apply it to some states, but it can also be different for every state. So it's just a metaphor we're using, let's say, for the fuel, because it's convenient, but it's something that is dependent on one particular, let's say, edge in the state space. So that's basically, a definition of the problem. The discounting is sort of also part of the, let's say, well, this is, depends whether this is given to you or this is something you decide, but this is related to something else. It's related to how much you prefer having a reward now over having it in the future, which, may also relate to, let's say, human psychology, or it depends on what problem you're dealing with. But so these are sort of this is sort of the difference. This gamma is something that has also, mathematically, it's important for us to be able to use this in infinite horizon formulation, but still having the bounded sum of future rewards. And you saw that we can make it, very close to 1, but still not 1, and that's sort of, important for the algorithms we'll be using to work out. So yeah, so they are two different things, but yeah, you're right that they will both, in the sort of sense that when we are normally using them, decrease the sum of reward, but in different ways. Yeah, basically, it's correct what you said there. Okay. Good. Yeah. Okay. Okay. Now we're coming to an algorithm. We will essentially do two algorithms that that will allow us to find the best policy. One is value iteration, which we will do today, and the other is policy iteration, which we will do next time. The value iteration itself is explained in the next Berkeley lecture together with the policy iteration. I think you will also deal with this during the labs. So let's look at that. It's not complicated. So you start with an arbitrary V0s, so you assign some values. So you can imagine, let's say, 0 values. And then this is the Bellman equation, but one thing changed here, and that is before it was an equation, but now it's an assignment, and that's basically the only thing that changed. So if we go back, right? This was the so if you can calculate the values for every square, you already know quite something about the problem. It doesn't directly tell you the policy, but you can actually extract the policy there. So it's called policy extraction. We will also learn how to do that. But so this is an equation that connects the value of one state with the value of any other state. And so it's a system of equations where you have as many equations as you have states. And you have also as many unknowns. Right, so those are the actual value functions of those states. So it's n equations with n unknowns, which seems reasonable. One problem is this max operator, which is a nonlinear operator. If you're taking a max of something, it's nonlinear, and that means you cannot employ the let's say linear algebra tools for efficiently solving these systems of equations. So that's why we switch to a iterative algorithm, which is this value iteration, and that uses this very same equation, but it gives there the assignment rather than the equation, which is here. And you just repeat it until convergence. So you imagine you basically assign 0 to every value, and then you do this step, which is basically one ply of expecting max, your current reward, and then this one ply of expecting max. And the point here is again that you don't have to go any further, because you can just use this one and assign it there. Those are your neighbors, let's say, in this state space. And yeah, and you repeat this until convergence, and it works, and it's proven to actually converge. So so Bellman update makes local consistency with the Bellman equation, and yeah, because it's locally consistent, it's also globally optimal. The convergence, it's a bit illustrated in the Berkeley lecture. We can also look into that a little bit, but it will not be really required that you can prove this. It's also a little bit technical, but we can have a look. Okay, one question for you. So what is the time complexity of value iteration? Yeah, it's not an easy question, but just try. to put it correctly, it's complexity of one estimation sweep, so one step of this. Okay, so and you will need as many sweeps as you do iterations, so it's a complexity of this one sweep. Yeah, so let's check the results. Yeah, so indeed, it's C. So why is it like that? So it's because you go through all the states in every sweep, right? And then in every state, so for every state, you're calculating the value. Those are the different states in the environment, you can imagine. And then, yeah, you're considering all actions because you need to max over them. And then the successor states, and now it depends, on your environment. But if you imagine everything is connected with everything, you can have up to, again, S neighbors. This is usually not the case, not in our map, because we cannot get from every square to any other square. But the upper limit is this. So it's S square A, but basically you can picture it like this. So this is one S because you're going over all the states. This is the A, and this is the other S because it's the S prime. So how many neighbors you have, and this gives you S times A times S, or this AS squared. All right. Yeah, the convergence. So basically, the idea is that the Bellman update is a contraction, which is a mathematical term, by a factor of gamma on the space of utility vectors. So thanks to this gamma, you know that with every step, the difference that you're considering will shrink, and that is what is called a contraction. That means that with every step you make, you're getting sort of closer to the solution. And because of the very same reason, there cannot be two different solutions, because because of the way that this whole thing is contracting, it will need to collapse to a single solution. So that's sort of the idea. Yeah, and and this gamma factor is an important part of it, right? Without that, it wouldn't work. But I think that's pretty much as much as we need to know here. So this is what I was talking about. So this is the Bellman update, and yeah, this is this kind of contraction that thanks to this gamma factor, it will become smaller over time. And this is basically the how you can work it out. Technically. And this, and part of this is something you will use in your code, is that you will basically, it's becoming smaller and smaller, and you will have to decide in your code when to stop, right? And this is basically when the changes are becoming small. So it's a, it can basically, it's it's an infinite procedure that goes infinitely closer and closer to the solution. But at some point, you have to basically decide that this is good enough, and that's basically this epsilon. Right. Demos. You will also get the code, and I think you have seen it also running in the Berkeley lecture. Algorithm. Yes, so basically it looks like this. So you assign this 0, and then you repeat this loop which is this basically this, one ply of expectimax. And, I believe in the labs, you will have the opportunity to try, and you can actually do it by hand. And and you will see that even in a couple of iterations that, you can do by hand, how it's rather quickly getting where you want it. So basically you do 3-4 iterations and you're already getting, where you want to be. And, you can then do 10 more iterations to make it sort of more, much more precise, the estimate. But for example, to sort of see what the best policy is, it converges in that sense quite quickly. But this is more maybe for the next lecture, where we discuss the differences between value iteration and policy iteration. This is called value iteration because we're iterating the values, we're incrementally updating the values. Policy iteration will instead choose a policy. It will also update the values as it goes, but it also sort of operates on the policies. It will change the policies. While here, you're going for the values, and eventually we will learn how to, once you have the values, how to extract the policy, which is something, what you really want is typically the policy. It's nice to have the value, an estimate, how much value I will get by following a certain policy. But what I really want, I want to know what to do in every state, and that's so the policy is usually my final goal. You can do this synchronously or asynchronously. So what does that mean? So that means maybe I can try to write somewhere. Let's use a different ink. So to update, let's say, value at time t of s, you're going to be using the values from the previous time step. So if you do it synchronously, you basically go through all the states, sort of and calculate the new values based on all the previous values. So that would be the synchronous way. The asynchronous way, that let's say I do it as follows. So let's say I decide to do VT S1, and let's say the neighbors of S1 are using, let's say, VT minus 1 S2. Okay, sorry for my writing. And VT minus 1 S3. Okay. And then let's say in the second step, I want to do, let's say I'm already at VT plus 1. If we imagine the async, now I want to do, let's say, S2. And so imagine that for this now I can use the, my neighbors are still S1 and S3. And so if so S3 hasn't been updated, right? So it's sort of it's still the same, but S1 has been updated from t to t minus 1. So I will take the most recent value, which is this one, but it's not the same as the one that it was before. So basically, I will use a newer value on the S1 than I will use for S3, which hasn't been updated in the meantime. So this would be the asynchronous way. It turns out that both are possible and both work. Actually, there are also variants of the algorithm which sort of deliberately use the asynchronous update. Basically, they pay more attention. They more frequently update the values for the states that seem to be more important for the problem. And we've seen something like this. Some kind of heuristics, like in chess, you were considering for some killer moves and these kind of things. So this can also improve practically the efficiency, but it will asymptotically, still be guaranteed to converge, provided that every now and then, basically, all the states get updated. So that means you cannot, just leave some states out and not update those values at all, because this will basically, the algorithm will not be guaranteed to converge anymore. But as soon as you every now and then also look at some states that you consider not important, it will still be guaranteed to converge. And so that's something that you can consider. Right, and so this brings us to the references. This is the book that was sort of for the first part of the course essential, and now we will be increasingly using this book, which is available online. So I invite you to download it and to have a look. Let me show you in a second. Yeah, if you have questions to the lecture in the meantime, then just write them to the chat. Okay, so let me share my screen. So this is from the Sutton and Bartow reinforcement learning book. And so if you are looking for the value iteration and policy iteration, you have to go to the chapter which is called dynamic programming. Okay, just that you're not confused. And this is the Markov decision process. Dynamic programming is a method from linear algebra for efficiently solving, for example, systems of linear equations, which is related to this problem. And here's policy iteration, something we will do next time. And here is the value iteration. And this asynchronous dynamic programming is basically about what we just discussed right now. With, if you do these synchronous or asynchronous updates. So yeah, this is the book, and it's freely available for download. And in the upcoming lectures, we will be looking at reinforcement learning. So this will become sort of the book, and we over the years we try to make the notation compatible, in particular with this book. So this is a good resource. Okay. So back to the overview. So as I said, for next time, please watch the Markov decision processes 2 from Berkeley using this link, and it starts with value iteration, and there will also be policy iteration, and yeah, then we basically do an interactive sort of a recap again here next Monday. Questions? No questions. Okay. Okay, so in that case, then thank you for the attention. And you see Philip in the afternoon at the lab, and I see you next Monday.
Thank you. Bye-bye.
Okay, thanks. Bye, everybody. Take care.